100 billion tons, so it's already mentioned a bit. To give you an idea, it's the size of 80,000 Olympic swimming pools, or maybe more accurate, it's 13 million garbage trucks filled completely. So it's quite a lot of material, and it's also the amount of urban biowaste that's produced in the European Union every year. So we're really good producers at that. But so far, I mean, we've been producing it for a long time, and most of the time it has been sent to landfilling in Europe. Still a significant part is still being landfilled with mixed waste, despite actions of the European Union and national legislation that's prohibiting it. So a lot of it is also sent to incineration, which is already a lot better than landfilling, but still, yeah, it's burning, let's say 60% water, which is not that efficient from a thermodynamical point of view. So then came composting, which is a huge improvement. So now we are recycling some of the organic matter and nutrients back to agriculture, to landscaping. But still it's an energy intensive process. So then we came to a big advantage, it's anaerobic digestion, which has been entering the market for the last 20 years, where we are still producing compost, we're still recovering nutrients and organic matter, but also instead of consuming energy, we're now producing energy. As Jochen said, we're now producing methane, which can be burnt to produce electricity, or it can be converted to natural gas. But still, it's only biogas. It's only energy and low value nutrients, organic matter that we're getting from it. So that's why the Volatile project came into place. We need to do something more. I mean, it's already a good improvement, but it's not what circular economy is. So we need to make better use of this. So I go quick over it because Thomas already did a nice introduction. So we want to go from a linear economy to a circular economy, and in the Volatile project, the VFA platform is how we want to get there. So again, as Thomas said, we're 21 partners from 9 countries. At the moment we're here, but I'm working mainly here in the small country of Belgium, in Ghent, a nice city. So that's us, a beautiful old building we're working in. So we're founded in the 80s of last century as a spin-off of the University of Ghent. By now we're 100 employees, and we had some affiliates in the USA, in Germany and in Japan. And one of our main tasks is building these anaerobic digestion plants. It's designed to treat urban biowaste. It's a dry digestion system, vertical reactor. Here are some examples. This one is in Mirandela in Portugal, so it's not that far from here, I think. And these are some plants of other Volatile partners in the project. So as I said before, it's anaerobic digestion, it's efficient technology, it's a proven technology. If you build one, you know what you can expect. You have a solid business plan around it. But still, it's a low value output. It's biogas, it's energy, and it's heavily relying also on energy subsidies for meeting these renewable energy targets. But without it, it's not economically feasible without subsidies. And a lot of these subsidies are expected to phase out in the future. So the VFA platform is the next level to treat this biowaste in a sustainable way. So in the VFA platform you can, there's sort of 3 steps. Of course, the production of the VFAs. If you don't produce them, there is no VFA platform. But also the extraction of VFAs is important, and then of course the conversion of VFAs into the target products that can be very broad ranges of industry. So first the production. So as both Jochen and Thomas already shortly mentioned this, we have anaerobic digestion as the backbone of the VFA platform. So you have urban biowaste, you have 4 steps in the biogas production. So you have first the degradation in the building materials, the fatty acid, sugar, and amino acids. Then in the acidogenesis or the acidification process, you degrade them into C3, C6 organic acids, some alcohol, some other components, and already some part of the chemical oxygen amount is going to acetic acid. And you also lose a little bit of the COD in the form of hydrogen gas. Then the acidogenesis phase is a further degradation of these medium chain organic acid to acetic acid, but also a significant part is converted to hydrogen gas. Then the final step in methanogenesis, you produce the methane, and roughly 70% comes from the acetic acid that's degraded to methane, but also the hydrogen that was lost is also converted together with carbon dioxide into methane. So to get from traditional anaerobic digestion to VFA platform, you need to shut down this fourth step, the methanogenesis. You don't want the production of methane anymore. And we focus on getting these C2 to C6 organic acids, the VFAs, volatile fatty acids. So how do we approach this? First of all, we want to characterize the waste that we have, and one way that we know of doing this is determining the biogas potential. And here you can see 4 categories: the wastewater treatment non-sludge, mechanical separated biowaste, so that's the mixed waste. Contains everything from plastics, every residue that's picked up, which separates mechanically the organic fraction out of it, which can be sent to composting or anaerobic digestion. Then you have the separately collected biowaste, so you separate it at home and it's collected separately, and also the separately collected food waste, which is more from industrial processes where you have higher purity. And this higher purity is clearly visible, so you see the higher the purity, the higher the biogas potential. And we did the same for VFA production. So that is this graph, based on more than 60 samples that we took from all volatile partners. And we see the same trend. So the lowest volatile fatty acid potential is also in the sludge, and the highest in the separately collected food waste. And the fact that this trend is exactly the same as we see in biogas potential is very good, because volatile fatty acids it's new, so we don't have much data. Also in literature there's not much data on what's the VFA potential of a product. But if we see the same trend, we can, biogas potential, that's already quite known. We can rely on this. If it has a high biogas potential, we can safely assume that it will also be an interesting product to treat in the volatile fatty acid platform. Of course you want to do the test, but it's a good indication to make a first shift in what products we want to use first. So we did not only determine the overall volatile fatty acid potential, but also what is in these volatile fatty acids. So this is a spectrum. And you see there's also some differences between the categories, and also inside the categories there's quite some variability from one source of, for example, VGFAs to another source of VGFAs. But there are some common trends, and that's acetic acid is always the main component in the C2 to C6 spectrum. But then in the other ones there's quite some variation. Especially in the sludge, you see that you have a lot of these isoforms of valeric and caproic and butyric acid, and it's only in the wastewater treatment from sludge that we found it. So it could be an interesting feature. Despite their lower overall yield, they have a very specific spectrum which might be interesting for some applications. Now coming back again to these overall anaerobic digestion cascade process. So an important thing is that it's inherently impossible to recover as much chemical oxygen demand in the form of VFAs as we could do in biogas because of this hydrogen gas. That it's not, we cannot convert hydrogen gas to volatile fatty acids as we can do it with methane. So that's a loss if you only look at volatile fatty acid production. But in the volatile project, we're not looking for a way to get rid of anaerobic digestion and convert it to volatile fatty acid. No, we want to integrate the two processes. And this is an example of how we could do this. So in a test that we performed, we started with the urban bio-waste, and we performed a mechanical pretreatment. So we did the separation of the waste in a more or less liquid fraction. It still contains quite some organic load. It's roughly 8 to 10% of total solids that we get in this fraction, but it's pumpable, it's easily miscible, and it contains roughly 1/3 of the total solids of the original waste fraction. We use this in the VFA fermentation process, and this way we can recover 50% of the total COD in the form of volatile fatty acids. So despite we only have 1/3 of the organics in it, these are the organics that we want to use for the VFA platform. These are the easily degradable ones, very short residence time, and we have a very optimal process. The remaining part containing more the lignin fraction, fibers, some larger material that's difficult to mix and pump. We still stand to the existing or new to build anaerobic digester, and we are able to recover the remaining 50% of the COD yield that we can obtain from the full VGFA fraction. Another way to show this is another test that we did. So we determined the biogas potential of bio-waste material. So this is what we get. It's what is theoretically optimal to be extracted with the current technology. Then we use the same fraction to treat the complete fraction for a VFA production. So in this case, we're able to recover 52% of the value compared to the biogas potential. So it's bio-waste, so it's very heterogeneous. So you can do it in a lab, but in a full scale, it will be very difficult to use a full fraction. So we again did the pre-treatment, and with this pre-treatment, we recovered 93% of what we could recover from the full fraction. So with this pre-treatment that I explained before, it's 1/3 of the organic matter is able to produce 93% of the full fraction. And with the remaining material, we can have this biogas production. So we still have this more or less 50-50 biogas and volatile fatty acids. So this is where we are now. We have 50-50, but of course, this is not the end point. I mean, the project started 3 years ago. We have, I think, made a good progress in these 3 years, but eventually, this is what we want to do in the end. I mean, the 28% that's going to hydrogen, that's theoretically impossible to recover, but we want to get as close as this 72% of the yield that's inherently contained in a bio-waste to also extract it to the VFA compounds, because this is where the value in the end will be. So this is what we're working on at the moment, and not only to optimize the VFA yield, but also look at the spectrum. So at the moment we're just having a spontaneous fermentation. It's focusing on optimizing the total yield, but the spectrum is still mainly defined by what you put in. Change the composition of the input waste, more fats or more proteins or more carbohydrates, you get a different spectrum. So what we're now also working on is can we customize this VFA spectrum? How can we tweak the process parameters to get maybe a more balanced spectrum of all components, or maybe we want to focus more on acetic, propionic and valeric acid, or for some processes we want more butyric and caproic acid, or we want to focus on having as much acetic acid as possible with only some minor other VFAs in it. So this is also a topic that we're now focusing on to tweak these process parameters and to get the spectrum that we want, and also keep it constant, so not producing one spectrum this week and another spectrum the other week, because there are small changes in input composition. If we want to be a reliable platform providing carbon source to other fermentation processes, we need to have a constant output product, and that's really an important step that we want to do. So now we have produced the VFAs, but okay, they're still in a liquid medium. We want to extract them if we want to use them for fermentation processes in bioeconomy. So we have, after the VFA production, we have the VFAs together with some undegraded macromolecules that's still in there, with the biomass fraction, of course, the bacteria are still in there. And we want to use a membrane extraction to get a concentrated VFA broth that's free of impurities, and then a residual fraction containing some organics that can also be sent to anaerobic digestion, or you have a process water that can be recycled in the process. So this looks simple, and Thomas also tells me it is simple. We just have to do it a cascade process. So first we start with the microfiltration to remove the suspended particles, so mainly the biomass and some undegraded material. Then we have the ultrafiltration to get out the macromolecules, nanofiltration to get the smaller ones out, and then you end up with unsaturated acids and monovalent salts, but we're still at roughly 20 to 30 grams per liter. So for carbon source, that's much too diluted. So then comes the reverse osmosis, in which we get out water and we get a concentrated product in the order of 300 to 500 grams per liter. And this water can then be reused in the process to dilute the incoming waste, and can recycle it in the process, so that you don't use fresh water each time, but you recycle the processed water. Yeah, these are some figures of the membranes that were used in the process, some of the nice products that we sent to Technalia, and some of the maybe nicer products that they got out of it. So you clearly see the effect of each cascade process, and then you get a very nice clear liquid. So some other, besides reverse osmosis, also a rotary evaporator was used in the lab to get this concentration factor, which is what you see here, and then the concentrated VFAs that were sent to the partners for further use. So I'm nearly there. So we have extracted them. We have a high concentration of organic acids, and also the only thing that has to happen now is to convert them in something that we can use, that we want. And in the project, we're focusing on three things. First one is the biopolyester, VHA, which Bruno from Biotrend will tell a little bit more about. We have the single cell oils, which Marcus will elaborate on in his presentation. And we have the omega-3 fatty acids, which Evangelos will tell a little bit more about. So now to end my presentation, I get back to one of my first slides, which is the 100 million tons of bio-waste, which we now, within the VFA platform, we don't regard as a waste material, but as a valuable resource for the VFA platform. So at the current state where we are now with the project, these 100 million tons of urban bio-waste can be converted to between 7 and 10 million tons of volatile fatty acids. And in turn, these could be converted to 2 to 3 or 4 million tons of either PHA or the single cell oils or the omega-3 fatty acids. So it's not waste anymore, it's a valuable input for a new platform technology. So thank you.